Okay, so let's get started. So we just finished lecture 6, the Fourier transform. So you should be, I think for the homework 6, the deadline. So it's due March 22nd. So we still have 5 days to go. So do you guys have any questions regarding the homework 6? I think it's all about applying the properties of Fourier transform. Okay, so if you have a question, if you have any questions, we can discuss this in the office hours. So let's continue our discussion of the discrete time Fourier transform. So we briefly introduced the DTFT last time. So here we can go over the basic definition again. So the DTFT is introduced to analyze the spectrum of aperiodic discrete time signals. Okay. So the definition is pretty much the same as the continuous time Fourier transform. And here, because the signal is discrete, so we replace the integration in continuous time by the summation in the discrete time. So the definition is pretty much the same as the Fourier transform. But because here we are looking at discrete time signals, which means the time index n can only take integer values. So this naturally introduces a periodic structure to the spectrum of DTFT. So for the DTFTs, the spectrum has a fundamental period with 2 pi. So this means when we visualize the DTFTs, we can only visualize the spectrum for any given period. And consequently, when we do the inverse discrete time Fourier transform, because of the periodic structure, so the inverse transform is given by the integration over any given period. So here we take the standard period, negative pi to pi. Okay, so this is the fundamental difference between DTFT and CTFT due to the discrete time structure. And last time we discussed this problem, so calculating the DTFT of the following exponential causal signal. So the idea is to follow the definition of DTFT, and in the end, after simplification, we need to evaluate a summation of infinite series, and this is a summation of, it's actually a summation over a geometric diminishing sequence. So applying this infinite summation formula, we end up with this very simple expression for the spectrum. So such a spectrum is very similar to the spectrum, continuous time spectrum for the continuous time exponential signals. So if you remember, if you recall, we have E negative AT UT. The Fourier transform is given by this one, 1 over j omega plus A. And now we are looking at A to the power of n un So the DTFT is given by 1 over 1 minus a e negative j omega. Okay. They look a little bit different. And this example is a window signal. Okay, so xn, the discrete signal, only takes value 1 within negative m1 to m1. Otherwise, it's 0. So it's a centered window. The length of the window is 2 times capital M1. Okay. So for such a window signal, discrete time signal, we follow the definition of DTFT. Now, because the signal only appears within the window, so following the original definition of DTFT, this summation, instead of summing over the entire time domain, we can sum over only this within this window. So it's from negative m1 to m1, and within this window, the signal takes a constant value 1. So we have 1 times this complex exponential part. So in the end, to calculate this DTFT, we just need to evaluate this finite summation, the summation over a finite terms. And notice that this sequence, if you view this as a discrete sequence, this is again a geometric sequence. It is e to the power of negative j omega to the power of n, well, n from negative m1 to m1. So this is a standard geometric sequence. So we can apply this formula. Which says that summation over such a geometric sequence r to a constant r to the power of n, well, the summation is over n from n1 to n2. This summation is given by such a big fraction number. So once you specify r, n1, n2, you can just plug in this formula, and then you will end up with this fraction number. Okay, so this is already a good kind of simplified result, but actually you can further simplify it, because you notice that there are lots of complex exponentials, and some of them look conjugate to each other. Like here we have positive j omega, here we have negative j omega. So this reminds us of the inverse Euler's formula. So actually what you can do is to taking out a constant factor. For example, for the denominator, you take out this constant factor, and then these two terms will become a pair of conjugate complex exponentials. Similarly, for the numerator, you take out this constant factor, and then the resulting two terms will also be conjugate to each other. Now, for these two terms that are conjugate with each other, you can apply the inverse Euler's formula. So this will give us something related to sine omega over 2. So here we have omega over 2. And similarly, for these two terms that are conjugate with each other, applying the inverse Euler's formula, we will have something related to sine omega times capital N1 plus 1/2. And these two constant factors, they cancel out. So in the end, the entire expression can be simplified to sine omega N1 plus 1/2 over sine omega over 2. So we can see that this spectrum, so this is the spectrum of the DTFT spectrum associated with such a constant, such a window discrete time signal. Now we can see that it is a little bit different from the continuous time. For continuous time window signals, we know that their Fourier transform corresponds to a sinc function. Right, so the sinc function is sine omega pi omega over pi omega. But for the discrete time window signal, the corresponding DTFT, it is not a sinc type function, because in the denominator we have sine, but for sinc functions we don't have sine in the denominator. Okay. So this is this implies that when we go to discrete time domain, the spectrum may be further perturbed by the discrete structure of the time index. But when omega is very, very small, like in the low frequency region, this sine is approximately omega over 2. So which means in the low frequency region, the spectrum still looks like a sinc function. Okay, so this is the discrete time window function. Again, we need to deal with summation over geometric series. And this is the formula that you want to refer to when you calculate DTFTs in the homeworks. And the other simple example is the impulse, discrete time impulse signal. So for such a signal, it is very easy to check that the corresponding DTFT is a constant 1. Why? Because according to the definition, now this is the formula from DTFT. And because of this impulse, discrete time impulse, it means that this signal only occurs at the original point when n equals to 0. So you only have one non-zero term in this entire summation, which is when n equals to 0. So when n equals to 0, you have delta n, delta 0 is 1. And then at the same time, this complex exponential part is also e to the power of 0, which is also 1. So you end up with a constant spectrum, DTFT spectrum for this signal. And this is the same as what we have for the continuous time impulse signal. In the continuous time, for the signal delta t, the corresponding Fourier transform is also given by universal constant. And like the CTFT, continuous time Fourier transform, the DTFT also has the following list of properties. And actually, the DTFT inherits most of the properties from CTFT, like linearity, conjugation, convolution, Parseval's theorem, time shifting. We will go over this one by one. And the only two properties that are slightly different from CTFT are the time scaling property and multiplication property. And this is due to the discrete time structure. So now let's go over these properties one by one. So most of them are very similar to the CTFT. Linearity is very similar. This is simply because the DTFT is also a linear operation. So when you have a linear combination of signals, two signals, the corresponding DTFT is also given by the linear combination of their individual DTFTs. And the conjugation is the same. So if you have a pair of DTFT transformation, then the conjugate, the DTFT of the conjugate of the signal is given by the conjugate of the corresponding spectrum. And again, if the signal is real valued, then the spectrum is conjugate symmetric. We also have this property for the continuous time signals. Time reversal, if we consider a reversed signal, discrete time signal, then the corresponding DTFT spectrum is also reversed in the frequency domain. So this is the same as the continuous time Fourier transform. Because all these properties are not depending on either the continuous time or discrete time structure. So they are the same, no matter we are in the discrete time or the continuous time domain. Time shifting is the same. If we have a time shift, discrete time shift in the time domain. Now here the time shift d is an integer, okay, discrete time. If we have time shift in the signal and the time domain, then this will induce a phase shift in the frequency domain. And the phase shift is given by e to the power of negative j omega times the time shift. So this is exactly the same as the continuous time Fourier transform. And this is the modulation or the frequency shift property. If we modulate the signal, discrete time signal, by a high frequency complex exponential signal. So now xn is multiplied by e to the power of j omega naught m. Then such a modulated signal has a spectrum given by taking the original spectrum and shift it to the right by omega naught. Okay, so this is basically the frequency shift property. We have the same property for the continuous time Fourier transform. And Parseval's theorem still holds here in the sense that consider the signal and its DTFT. Then the signal energy that we collected in the time domain, right? On the left-hand side, this is the signal energy. This is exactly the definition of signal energy for discrete time signals. This signal energy equals to the energy that we collected in the Fourier domain, frequency domain. And notice that because the DTFT has a periodic structure with 2 pi, so this so when calculating the energy in the frequency domain, we just need to take integration over 1 period. So it's from negative pi to pi. So this shows that energy is preserved is invariant in both domains, either the time domain or the frequency domain. Okay, so these are the same as the continuous time case. Okay, so time scaling is a little bit tricky because we in the discrete time domain we have to make sure that all the indexes are integers. So it's actually we need to pay a little bit more attention. So in continuous time domain, we can scale the signal by an arbitrary real number, right? Because the t, small t, is can take any continuous real values. But in the discrete time domain, we can only scale the indexes by integers. So this is how we do the time scaling in the discrete time domain. It is actually very intuitive. For example, we will do time expansion in this way. So for an integer k, we want to expand. We want to expand signal by a factor of k. So if we are looking at the continuous time domain, then we will do xt to xt divided by k. Right here, the factor k can be any real number. But in the discrete time domain, you have to restrict everything to integers. So intuitively, you want to do, of course, here, k must be an integer. Intuitively, you want to do xn to xn n over k divided by k in the discrete time domain. So well, k is an integer, certain integer. But it is possible that this fraction number may not be an integer, right? This n, both n and k are integers, but their ratio may not necessarily be integer. So we have to, when we do this expansion, we have to do a zero padding to make sure we consider we did not introduce any meaningless time indexes. So if n happens to be a multiple of k, meaning that n over k is a valid discrete time index, then we can just assign the corresponding value to the signal. Otherwise, if n is not a multiple of k, then we will just pad a 0 to the signal. Okay, so this means when we do time scaling, this is how we do time scaling in the discrete time domain in general. Now, once we are given such a factor, and we follow this process and create this time scale signal, we call this x tilde n. Then we will look at how the DTFT of this signal is related to the DTFT of the original signal. Now the result we have is that for such a time-scaled signal, its DTFT is given by taking the original spectrum x e j omega, capital X e to the power j omega, and multiply this omega by k. So essentially, if you are doing a discrete time scaling with factor k in the time domain, and you will have this will give rise to a frequency scaling in the frequency domain, and the factor is 1 over k. So instead of having 1 over k in the time domain, we have k, factor k in the frequency domain. And this part is the proof for this relation. Yeah. And the proof is actually very straightforward. We just follow the definition of this signal and plug it into the formula of DTFT. And in the formula of DTFT, we are summing over all the discrete time indexes m. But you realize that for this constructed time scale signal, we only have non-zero values when n is a multiple of k. So basically, the summation is only over m instead of n. Well, this m is such that whenever n can be written as an integer m multiplied by k. Now, once we do that, so we can calculate the corresponding summation series. Now, at these locations, the x tilde equals to the value of xm. And this is exactly the definition of the DTFT of the original signal, however, with a scaled frequency index. We have k omega instead of omega here. So that's why it finally gives us the DTFT spectrum of the original signal, but with a scaled frequency index. Okay, so this is the time scaling. A little bit tricky. And the multiplication property, this is very similar to the continuous time Fourier transform. Basically, multiplication in the time domain corresponds to a sort of like a circular convolution in the frequency domain. So first of all, this part, it has a convolution structure, right? You have theta, omega minus theta, d theta. So this is a convolution structure. And we call it circular convolution because we are doing this convolution over a unit circles, 2 pi, 0 to 2 pi. But in the continuous time case, we have convolution instead of circular convolution because we don't have a periodic spectrum in the continuous time case. So there the integration is over infinity to infinity. Okay, so this shows that multiplication in time corresponds to a convolution, circular convolution in frequency. So now, on the other hand, we also have this convolution property where the convolution in time will lead to a multiplication in the frequency domain. And this is exactly the same as the CTFT.
On that multiplication slide, was the integration from 0 to 2 pi?
Yes, this is from 0 to 2 pi or any other interval that spans over 2 pi.
Okay, thank you.
Yeah, this is because for all these discrete DTFT spectrums, they have a fundamental period with 2 pi. Yeah, so you can either take 0 to 2 pi or negative pi to pi. Okay. And the convolution property is pretty much the same as the continuous time case. If you have a discrete convolution in the time domain, right? If you consider xn convolution with hn and denote this convolution as yn, then if you take DTFT on both sides of this equation, now for the yn taking DTFT becomes the corresponding spectrum, capital Y. And for the right-hand side, the DTFT of this convolution signal, it simply becomes the product of their individual DTFT spectrums. So this property is also the key property of the DTFT. So similar to CTFT, we can also apply DTFT to analyze linear and time invariant discrete time systems in the frequency domain. Okay. And this is the proof for this property, which is the logic is the same as the proof of the continuous time case. You just okay, so here you start with the DTFT spectrum of Ym. Now, by definition, this is given by the DTFT definition, this is given by sum over n Yn times e to the power of negative j omega n. But Yn is given by the convolution in time, right? So specifically, you can replace Yn by this specific convolution. So this big parenthesis is essentially Yn. And because Yn equals to this convolution, so you have Yn equals to. Now this is the definition of discrete convolution between x and h. So the first step is basically writing down the definition of DTFT for Yn, and then plug in this convolution formula into this Yn. And then you have this double summation, so you can exchange their order. And then you will realize that by exchanging the order, this part is a standard DTFT formula for a shifted signal, Hn minus k. And then by the time shifting property of DTFT, this will correspond to the spectrum of H multiplied by such a phase shift in the frequency domain. Right, so this is by the time shifting property. And then this phase shift together with this X, together with this outer summation, will give us another DTFT, this part. Okay, this phase shift combined with this outer summation over xk actually corresponds to the definition of DTFT for xn. So this is exactly, by definition, this is exactly the DTFT spectrum of X. So by doing so, we can show that if we analyze discrete convolution in the frequency domain, we can get rid of the convolution. Instead, we have multiplication of the spectrum. Okay, so we can, by the previous convolution property, we can apply this DTFT to analyze discrete time LTS systems. So essentially, if we have a discrete time LTS system, then the output, we know the output is given by the input convolution with the impulse response. So this is the time domain system equation. But in the frequency domain, we have the corresponding DTFT spectrums given by X ej omega times H ej omega. And we call this capital H the frequency response of this LTS system. Now it is basically the DTFT of the system impulse response. And from this equation, we can see that this capital H is basically the capital Y over capital X. And for this equation in the frequency domain, we can, because everything is a complex number, all the spectrums are given in complex numbers in general. So we can have two sub-equations where one only concerns about the magnitude. Like the magnitude of Y equals to the product of these two magnitudes. And also the other one concerns about the phase. Phase of Y is the sum of these two phases. So these are due to the fundamentals of complex numbers. In many cases, when you do programming and trying to visualize these magnitudes, sometimes you will find the numerical values of these magnitudes are very large. So sometimes we use the logarithm to reduce the numerical scaling of these magnitudes. So if we take log on both sides, we have log Y. Now this product becomes summation of their corresponding logarithm values. And these are the, so for a continuous time signal, we know that the Fourier transform is, oh, actually, we can put these two together. So for both continuous time Fourier transform and discrete time transform, if the underlying signal is real valued, we know that they satisfy a conjugate symmetry property, right? If it is a continuous time, then we have x j omega equals to x conjugate negative j omega. If it is discrete time, we have x e j omega equals x h conjugate e negative j omega. And these two equations, actually, they imply that, first of all, because they have, these are conjugate to each other. So if we take their magnitudes, we know that conjugation does not, for a complex number, conjugation does not change the magnitude. So basically, once we consider the magnitude spectrum, the magnitude spectrum will look like a symmetric picture. Okay, so this the magnitude spectrum is an even function. You can see that. But the phase spectrum is an odd function because of the conjugation. So this works for real valued both continuous time and discrete time signals. And moreover, for discrete time signals, since we know the DTFT has a periodic structure, so we only need, for this one, we only need to visualize the DTFT for a given fundamental period. Okay, and so moreover, in practice, we usually use the dB units to plot the magnitude plots. So as we mentioned in the previous slides, sometimes these magnitudes becomes numerically very big, so we can transfer them into the dB scale by taking 20 times log 10. So why we define dB in this way? Well, you can see from this table. So these are the original scales, like the magnitudes, original numerical magnitudes. And these are their corresponding dB scales. So you can see we actually define the dB so that now, because of the logarithm, even the magnitudes has a very large numerical value. The corresponding dB scales varies reasonably small, so you can plot everything clearly on the plot. Yeah, I think this is a convention, so that square root of 2 will give us 3, and square root of 2 corresponds to, if we square the square root of 2, it will give us a factor of 2. So it means whenever the power, because the power is the magnitude square, right? Whenever the power is increased by 2 or decreased by a factor of 2, then the dB scale will be increased by 3 or decreased by 3. So that's why in the dB scale, we always care about this 3 dB criteria. So if the scale is reduced by 3 dB, then that essentially means that the power reduced by half. So for example, this is a dB plot for a certain DTFT spectrum magnitude response. And in engineering, we often introduce the 3 dB bandwidth, which means starting from the peak, the highest response, you look for, you consider the bandwidth where the response is reduced by 3 dB. So in this case, this is 0 dB. Now reduced by 3 dB will give us -3, so it's around here. And then you draw a horizontal line, so the bandwidth is about this wide. So within this band, the response is within the 3 dB scale, which means that within this band, the frequency magnitude response is now more than 1/2 of the highest response, the peak response. It's not 1/2, sorry, it's 1/√2. So it means that if you look at let's say this is 0 dB, and then you look at -3 dB. So this within this band, let's denote this as omega-2. This means this one equals to 1/√2 times the highest response. Okay, so you define the 3 dB bandwidth in this way. Okay, so all these are just definitions that we may be used in the lab sessions. So when you plot the y-axis for the magnitudes, consider use the dB instead of the original scale. Okay, so now because of this convolution property, we can utilize this convolution property to analyze the discrete time systems. So in continuous time systems, we discussed that Fourier transform can be used to analyze differential equations. So similarly for discrete systems, we can use the DTFT to analyze difference equations. So for example, we can consider the following discrete time system, which is given by a difference equation. So let's look at this system. The output Yn depends on the following. The first part is a linear combination of the input. It's actually, so here we are looking at all a linear combination of inputs starting from the current time up to the previous m time indexes. So we are looking at a history of window length of m. And then also depends on the history of y. Okay. So if you move this part to the left-hand side, now this is a standard difference equation. Standard difference equation. And for such a discrete time system, we want to find out the corresponding impulse response. So first of all, this is an LTI system. We can show that it's an LTI system. So for LTI system, it must have an associated impulse response. Okay. So the way we find out this response is to leverage the system equation in the frequency domain. Yeah, so we have this system equation in the frequency domain, which implies that h is y over x. So we can just take DTFT on both sides. So similar to the continuous time case, after taking DTFT, all these history terms, now because they are time shifted versions of the signals. So by the time shifting property, this xn minus m will become the original spectrum with a phase shift term. Okay. So it's basically by the time shifting property. And similarly for the y terms, so again by the time shifting property. So in the end, we can get rid of all the difference equations, and instead we only have spectrum of x and spectrum of y, and they are scaled by different complex numbers, coefficients. So we can rearrange this equation. So we have capital Y times this big complex number equals to capital X times this big complex number. And then dividing Y over X, we obtain this DTFT of the impulse response. So capital H is Y over X. And from this equation, Y over X is given by this fraction number. And in some cases, you can further simplify this fraction number and maybe find out the corresponding inverse signal, the time domain impulse signal, by looking into the table of discrete time Fourier transforms. But the key idea here is to transform the system into the frequency domain so we can get rid of all the difference equations and instead only have the spectrum of y and x. And here's an example, a more concrete example where we have this system equation, difference equation. And we can follow the previous slide to find out the impulse response of the system. Now, basically taking DTFT on both sides. Okay, so this is Yn becomes capital Y, and this is 1/2 times capital X. Now, for this one, by the time scaling property, here we have a time shift of 1. So this will cause a phase shift in the frequency domain. So it's this phase shift component times the spectrum of X. And then for this one, it's a phase shift times spectrum of Y. So you basically do this one by one. And then you just rearrange all the terms and solve for the ratio Y over X. So in the end, this ratio gives out this fraction number. And this is the DTFT spectrum of the system impulse response. So the standard step is to first convert the signals in the time from the time domain to the frequency domain, and then leverage the system equation in the frequency domain. So the system equation in the frequency domain is very, very simple. It's a direct multiplication instead of convolution. And then from there, we can work out the signals, any of the signals, by solving this simple equation. Now, once we have the spectrum, we can do, for example, once we have this spectrum, we can do a partial fraction expansion and then find out the inverse signals by looking into the table of discrete Fourier transforms. So here we usually in the examples that we are considering in this course, these two pairs of discrete Fourier transforms will be frequently used. Again, we are looking at exponential family of signals. Okay, this is another example of a difference equation. Okay, now you can follow the same process and find out that the corresponding DTFT of the system impulse response is given by this fraction number. So remember that here, this omega is the variable. So it's a function of omega. So this is 1 minus 3/4 e negative j omega plus (1/8) e negative j 2 omega. So you can see that the denominator contains 3 terms, and in particular, we have a 0th order term, which is constant. And this is like a first order term because it's the e j omega to the power of -1. Now this is like a second order term because it involves negative e j omega to the power of -2. So the denominator can actually be, so if you want to simplify this a little bit, the denominator can be factorized into 2 factors. Okay, so you have 1/8 can be factorized into 1/2 times 1/4, right? And 1/2 plus 1/4 is 3/4. So therefore, you can kind of do the factorization, factorize them into -1/2 and -1/4. Right. So these two multiplied together gives you this number, and in particular, the summation of these two coefficients will give you -3/4. So this means that you can factorize the denominator into using these 2 factors. So it's 1 minus 1/2. Okay. And then you have a standard fraction number that can be factorized. So you can do partial fraction expansion and following the standard process of partial fraction expansion, you can factorize this fraction number into following smaller ones. Okay. So it turns out that you can find out K1 is 4 and K2 is -2. So in the end, you can factorize the spectrum into these 2 smaller spectrums. And then you can leverage the table of discrete Fourier transform. So you can see that both of these 2 fractions, these 2 spectrums falls into the form of the first one. Therefore, following this pair of DTFT transformations, we can find out the corresponding inverse signal in the time domain. Okay. So for this one, 4 is a linear scaling factor, so it's preserved here. So it's 4 times. Now this signal, from that table, we can figure out such a spectrum corresponds to this signal. Okay, and then this spectrum corresponds to this signal. Okay. So the process is the same as what we have done in the continuous time Fourier transform. We have essentially you analyze the system equation in the frequency domain, you figure out the spectrum, and then you look into the table, do a partial fraction expansion, look into the table, and figure out the signal in the time domain. So there's no need to evaluate the inverse transform by hand. So you can do this for this example in a similar way. Yeah, and let's actually do it very quickly. For this one, you don't actually need a partial fraction expansion. Right? So once you have this spectrum, and now you look at this table. Can you figure out the inverse signal for me? So the denominator is already a single factor, so there's no need to do partial fraction expansion. But the denominator has two terms, but the numerator has two terms, whereas here we only have one. So how do we leverage this transformation pair to find out the inverse? Any thoughts on this? You have two terms in the numerator. Here we have only a single one. Right. So this is a little bit tricky because so here you need to decompose it into two terms. Let's do a decomposition. And now this one falls into the standard form. It's just scaled by 0.05. So this is very easy to do. So the inverse is 1/2, is 0.05. And for the rest of the fraction number, you actually find out that A is 0.05. It's right here. So this is 1/2. A is 0.05, 0.5. So it's 1/2 to the power of n un. Right, so the first one is very easy. Now what about the second one? We have a complex number in the numerator instead of a single constant. So for the first one, we can just think of that as a linear scaling. So how do we do for this for the second one? So this part, right? I would say this part falls into this standard format, right? So it's constant over 1 minus something times e to the power negative j omega. But we will have this additional complex factor. So how do we address this one? Given, yes, do you have any ideas?
Can you multiply the top and bottom by e to the j omega?
For this one, if you do that, then you have 0.25 over this one times e to the power of j omega, right? And then this denominator will become different from this one. Right. So you can think of this, yeah, so this is like whenever you see e to the power of j omega in the frequency domain, always think of the frequency time shifting property. Okay. So we can view this as, well, the red part. For the red part, we can find the corresponding signal in the time domain. But then how do we generate this blue part? Well, we can think of that signal in the time domain is shifted by certain time index. And that time shift by the time shifting property will induce such a frequency, will induce such a phase shift in the frequency domain. So what we do is that, first of all, for the red part, we can follow the same process and find out is 1/4, which is 0.25, 1/4, and now the A is this one, right? This is what we will have if we only have the red part. But then in order to introduce the blue part, the only way we can do this, so basically you need to multiply the spectrum by such a complex exponential component. And this can be only done by the time shifting property. So you look at the time shifting property. Well, if you want to introduce such a vector, you need to shift the signal by d. And you look at this one, d here is just 1. You need to introduce such a vector with d equals to 1, which means you need to shift the signal by 1 in the time domain. So instead of having this, you actually have, you need to shift the signal by 1. So you have 1/4, shift by 1, and shift by 1. Right? So it's a combination of time shifting property and also looking into the table of DTFTs. And this can be, you can further simplify this by absorbing this -1 into. So this will introduce a factor of 2. So you can cancel with 1/4. So this is how you deal with these inverse transforms. You need to be sensitive to this fundamental properties of DTFTs. But I think once you see more and more examples, you will have a experience. You will have an intuition of how to handle these different situations. So for this one, right, we just handle it one by one, and this factor can be addressed by the time shifting property. Okay, and in this example that we just talked about, there's it's quite standard. Once you do a partial fraction expansions, both of these two are quite standard. So you look into the table, and you can immediately find out result. But if the numerator is more complicated like that, then you should also consider the time shifting property. And this is the last example where we have this. Okay, if we feed this signal to the system given in the previous slide, then what is the corresponding output? So from the previous slide, we have such a system, right? And from the previous slide, we have worked out the system response. So now we are given this new input signal. So to find out output, we just refer to the system equation in the frequency domain. Right? Otherwise, if we do this in the time domain, then we will have to take discrete convolution between this one and this one. And this is a very complicated task. But if we consider this in the frequency domain, we know that the input and output is given by such a simple equation. And in the previous slide, we already find out the system response, capital H. So this is the capital H that we obtained from the previous slide. And now we are given this new signal. So first of all, from that table, DTFT transformation table, we can find out the DTFT of this signal. Again, it's a standard exponential signal. So the DTFT takes this form. Okay, so you have this capital X, now you have this capital H from the previous slide. You just need to multiply them together. After multiplication, you end up with these two fraction numbers. And then you do, for the first one, you can do a partial fraction expansion. So the first fraction number decomposes into these two. And the last one, we can keep it because it is already in the simplest factorized form. So the last step is so this is basically the DTFT of the output signal. And we need to find out the signal. So we just need to find out the inverse of this DTFT. So you can see that both of them are standard DTFT in the table. So the first two, we can use the first pair of DTFTs in this table. For the third one, because the denominator has a square, so we can refer to the second pair of DTFTs in this table. Okay. So in the end, you look into that table and you can work out all of the inverse signals. So they look like this. And UN is a common factor. Okay. So this is a very much simpler approach compared to directly calculating the discrete convolution between X and this H. We know that discrete convolution is a very painful task. So here, once we do DTFT, we just need to look into the table and do an inverse. Okay, so this is this finishes lecture 7. Most of the materials in this lecture are pretty much similar to the Fourier transforms. So I would say these two, they follow the same idea, almost the same idea, except that we are considering discrete signals in this lecture. So homework 6, homework 7, the main techniques are pretty much the same. So I think I can, so we have 9 minutes left. So So I want to ask if you have any questions or concerns about the homework 6. Maybe we can have a brief discussion in the rest of the 10 minutes. You have any questions? Like all of these are following, utilizing the basic properties of Fourier transform. This is time shifting, differentiation property, convolution property, and this one is modulation. Okay, like for this one, now this one is modulation because you can decompose this one into 2 exponentials, and each of them will, you can handle each of them using the frequency shift property. But for this one, it's a convolution, so you can think about convolution property. And basically, each of this signal is a sinc type signal. So the corresponding Fourier transform is very simple window signal, window spectrum. So you should be able to you should be able to handle that easily in the frequency domain. And this is a standard cosine signal. Yeah, I think all of these are covered by the lectures. Okay, so if you don't have if you have no questions, so I think I can stop here today. And I'm not able to hold office hour today because I have somebody visiting me. I need to host them. So if you want to schedule a meeting, send me an email. I'm available tomorrow. Send me an email with your available time slots. I will respond to that. Today I will not be able to hold office hours. Okay, very sorry about that. Okay, so if there's nothing else, I guess I will stop here. And the midterm 2, I proposed to do that on April 5th. You can check that. April 5th, we have plenty of time to go over. April 5th is right here. We have about 2 weeks, okay, to go over the lecture 8. And for the rest of time, we can look at homework examples, homework problems, and do a review lecture and do office hours. Okay, so please be aware of that. Okay, so I will see you guys next week. And if you need an office hour, please send me an email. We can schedule that. Okay, see you then.
Thank you.